So today I'll be talking about time series prediction, largely four or five directions. So first we'll introduce what time series is, walk through what sort of constraints we can place on time series prediction so that we can feasibly model or feasibly design a parameterized model that we can estimate and which is close to the reality, but still something we can compute and not something completely based on noise. Moving on, we'll talk about how exactly those are formally structured and how we can, if we have non-stationary processes, how we can incorporate that information into the thing, into the initial model that we have. So first question that I want to start with is, what is the time series? Time series is basically a collection of data which is indexed in time order. So samples are coming in one after the other, and they keep coming. These don't necessarily have to happen in periodic intervals. They can happen arbitrarily, but as long as they have sort of a temporal component to it, it ends up becoming a time series. And looking at these three examples, we can see what time series would generally look like, and what I would, in the context of this lecture, what I'm calling a time series. For example, the COVID cases in the US was a time series. It was steadily, you're getting samples steadily, not necessarily periodically. You won't get them updated on the weekends or the holidays, but they would still get updated and become a time series. They can have a shorter time scale. They can have a longer time scales, like over the decades, how portfolio cases have progressed, or the number of them, and how this series varies in time. And another one is the Dow Jones Industrial Average and how it gradually increases in time. Okay. I'll just keep going unless you have some. Do you have any
Sorry to disturb you, Professor.
Nope.
We can't see you.
There was somebody saying.
Yeah,
We can't see you.
he's saying you can't see.
We can only see the classroom.
Yeah, okay. I don't know how to work the camera. A quick recap for people who just joined. Time series is something with samples recurring in time over and over again. You're measuring them. They don't necessarily have to be periodic. And our interest is how we can say, how we can be informed with the data that we've observed. Can we make informed predictions about the future and say what the time series would look like when we move forward in the future? Would it be increasing or decreasing? In essence, can we forecast a given time series? So, and now I wanted to define forecasting. So time series, just as we talked, can comprise of any sorts of measurements that you make indexed in time. So that can happen with the daily high and low temperatures. It can happen with the air quality, that is one of the projects. It can happen with the stock prices or exchange rates, which is another project, or something like a weekly precipitation or whatnot. And this leads us to, so we're collecting a lot of data. We have a lot of observed samples. With these observed samples, can we make reasonable deductions about the future? And that is forecasting. So, this is an example of forecasting, precipitation in Pennsylvania. And you can see that in here with the blue line, they tried to model it as a linear model, and which is steadily increasing. It might not seem like a very good model, and we'll get to discussing how can we build more accurate models for these sorts of problems. So, moving forward, I wanted to walk through an example of how, or build some intuition on how forecasting can work. For example, we sample 4 data points in time. Time right now is arbitrary, but it is gradually increasing. We sample 4 data points, and we think that we'll keep things simple, and like the previous example, we'll fit a linear model to this. And the linear model says that this might be a steadily decreasing trend. But of course, these are 4 samples, not very informative, so we can go ahead and add a whole lot more samples and keep collecting data in time, for example, from a sensor or something. And you can see that now, well, before the linear model said that this was decreasing, but now, if you fit a linear model, that would sort of tend towards increasing. And when we've collected more sample, although there is some variation in the time series, we can still appreciate that the linear model is doing a pretty reasonable job. Now, moving on, if we collect a whole lot more data, say 1,000 samples, Now we can see that this time series, well, linear model is doing a good job. This is awfully looking a lot like a quadratic function here. So we might want to update our model or our based on the observations that we have, we might want to update our understanding of the model that can represent this time series, and we might call a quadratic function here to be a good enough fit. Now, this almost seems to fit perfectly with some added noise, which is because how I generate this function. But moving forward in time, we can add some new, so a variation occurs and your new samples are starting to deviate from the model that you have. And if you collect a whole lot more samples with another sort of a quadratic that is sort of decreasing, you notice that your initial understanding of the data was not sufficient to accurately model the whole thing, and you need to update your model again. And so with the observations that we have and the assumptions we have made about the data, we're trying to build model, which is why the assumptions we make about regarding the time series are critical. If we assume it to be linear, if we assume it to be quadratic, if we assume it to be a sum of different linear terms, all of those would have an influence on how accurately we can model the time series. And just like everything in real life, there will be some noise added to the time series, and how we model that noise is also going to play an important role in time series prediction. Now, this leads, so now that we have an intuition of what time series is and forecasting is in context of this lecture, we'll move on to stationarity and a representation theorem called wall representation. We'll get to that. So modeling time series is somewhat tricky, and we're sampling these time series in time. But what would it take for a time series to be considered stationary in time? A stationary time series can be considered to be, for example, the Costco hot dog prices. They stayed at $1.50 for a few decades. This is a time series that does not vary in time, strictly stationary. So this can be considered a stationary time series. But or mathematically, a stationary time series is one whose mean invariance or any of these higher order moments, they do not change with time. And since these higher order moments result from a probability distribution, a more general thing to say would be with time for a time series whose probability distribution function does not really change would be considered as a stationary time series. So probability density function can be a function of any other variable except for time. That could be considered as a stationary time series. All right. And why would we want to work with stationary time series is it becomes very easy for us to model the time series if it is stationary or in the bounds of what we define it to be stationary. If that is stationary, then we have a constant or fixed distribution that we can work towards estimating. And that's what this lecture is primarily about. So any time series that we have is not stationary. We'll try to do things to that time series so that it becomes stationary, so that the model that we have built can be applied to that time series. All right. So getting into the math of things, and this is how most of the lecture will be. So a time series is defined for this lecture with these curly braces and xt or pd or whatever. So before moving forward, the most true form of stationarity is the strictly stationary time series. A strictly stationary time series is one whose cumulative distribution function or probability density function, PDF, they do not change in time, just as I said. So they are not a function of time, and the series X would be strictly stationary if all the distribution of samples in the n times that you observe is the same as the n times in the future that you observe with a lag, and n here can be like anything. So if you observe the series now, you observe it a year later, a decade later, it has the same distribution. And that is when it would be strictly stationary time series. Some examples can be a constant function, x equals to y. This is always stationary, no matter when you measure it. Cosine t plus y, that would always be stationary given for all real number if you have a fixed period. But this brings a question. While this is very helpful, parameters don't change and everything is nice and fixed, is this useful? Yes.
find the stationary relationship that might be more useful instead of finding stationary, variable or stationary value. Like if we can find a stationary relationship between the weather temperature and the stock price, that is still stationary, right?
So relationship between two variables, like the covariance is between them would be stationary?
Yeah, kind of.
That's what we'll get to as the next step. So, so this brings a question like, is a strictly stationary time series useful? Well, it is helpful because it helps us model things with parameters and statistically and everything, but this is not how the real world operates. Distributions change and evolve over time. Stock market prices is an example. They're very fluctuating, depend on a number of variables, and the distribution from which their numbers would be hypothetically coming is not going to stay the same. So that, okay, this is just a visualization of the time series. This brings us to the nth order stationary time series, which is what sort of close to what you were hinting. In this, we sort of relax the assumption of the strictly stationary time series. Here, the n is no longer a set of all real numbers, or all natural numbers. Instead, it is a fixed set that you define over a range. So this distribution is now going to stay constant in a fixed time interval that you have defined. So a reasonable assumption here of this.
So is this the same as like a periodic signal or like series?
Not necessarily periodic. It's what this is saying is that distribution in the window that you're seeing is not changing as much. Okay, or it's strictly not changing. So an example could be temperature of this room in the last 10 seconds, or that would be nth order stationary, but not strictly stationary, because if you look at it at all times, like maybe at the night it gets colder when people are not here or something like that. So if you're defined, what this means to say is with the assumptions you can make about the observation window of the time series, you can start placing your constraints on time series that, oh yes, the distribution might stay constant in the window that I'm seeing. Okay. Cool. So we can take a step further. This still requires the distribution to stay the same. And this means that all the higher order moments and everything will be the same. We can relax this requirement a little bit and say that we're not going for nth order stationary series. We'll instead go for what is called as a covariance stationary process system. As the name indicates, their covariance is not a function of time, their variance is not a function of time, mean is not a function of time, but other higher order moments can be. So this is a more relaxed view of modeling a time series. And this is what we'll primarily be using. So the time series that we talk about in this lecture, they'll all be covariance stationary processes. And a key thing to note is all of these three, for any x drawn at t, are independent of time. Yes.
Stationary process.
Sorry, what?
Is this the same as a wide set stationary process?
Not aware of that time series. It's like, is it a? Can you define the time series?
So the WS is basically saying, correct? Yeah.
Oh, okay. All right. And
Exactly what it is.
oh. Another thing, how we can measure stationarity of a time series is through the autocorrelation function, correlation of a time series with itself with a lag copy in the past or in the future, and this value should stay again constant. This brings us to the first poll for today, and this is the, so I have added a 0 on the poll. Yes, I assume people would sort of have an equation. I have a more detailed slide on that.
Trials.
Yes, 400 trials, number of trials.
Great, so that is.
Oh, good. Thank you. So we'll move on. The correct answer is the first two. They have a distribution that would not change with time. For the other two, which are more likely to be praised, but their distribution would change with time, and hence they're not stationary time series. All right. So now we'll get into more formally defining what stationarity is. Now, first is why would we look at stationary time series? Stationary time series are very convenient for us to work with. They're, a lot of literature exists on them already. With their nice properties, it's easier for us to parameterize and model them and then optimize our models. These sorts of covariant stationary processes that we talked about are a reasonable enough compromise between what the real world is and what we can actually feasibly model. So that's also nice. And one way to think about it is we can have a more informed and less constrained time stationary model. And this might be able to very accurately model a real time series. And this is what we're after. One case or two cases that I have for modeling time series is, for example, future prices. We assume, in case of stock market, we assume that the future price that you'll have is a running mean of what you've seen before. It is a very simple model, very easy to estimate. You have just one parameter. And the other model is a little more complicated. We assume that the future price is now multivariate. It depends on more than one thing. And stock market can depend on the previous prices, like before. It can depend on the profits of a company. It can depend on the geopolitical scenario, oil prices, and whatnot. And whatever still remains, we can then model that as some stochastic noise. In between these two cases, clearly one is more representative or a rich representation of the time series, but still neither of them is perfectly accurate, and we still have this noise component that we cannot account for. Skip 2 slides. So with the stationary processes, we'll start thinking about how we can model them. And one step in that direction is the Wold representation. This is named after the person who discovered it, Herman Wold. So Wold representation theorem states that any zero mean covariance stationary process, so covariance process that we talked about, but with a zero mean, you can decompose that as a sum of two different time series, V and S, where V would be a deterministic process with constant coefficients that don't change in time. And S is a moving average process of the error or stochastic term that you have. And these are again weighted by the size, and these are moving average weights that you have associated with them. And eta here, it comes from the normal distribution with zero mean and sigma standard deviation. So this is just one way of decomposing the series that you had, which was a combination of some component that you can predict and some noise. Putting those two separately and assuming them to be additive, and you can say now that the deterministic part that I can model is V, part that I cannot say much about is actually weighted, so we can say a little about it, but it still has some noise component to it, and that is linear white noise. So because we represented this time series as a sum of two distinct time series, we can start thinking about the properties that each of these individual decomposition components have, the deterministic and the stochastic. For the stochastic component specifically, we can apply these constraints where we say that the weights are stable, which is another way of saying that they don't explode to infinity or they don't keep increasing in time. There are some conventions associated with this where white noise is normal, IID. Conventionally, the first weight for the noise is set as 1, and it's also correlated with the drawn samples that you have. So the samples that are the deterministic time series that you have does not vary with the white noise. So why would we? Yes, this is deterministic. So why would we want to do this? Why is this sort of representation or this sort of decomposition helpful? Well, why this is helpful is we had one time series X, which was varying in time, which had some noise component to it, But now we have separated out these individual components into things we can actually estimate, and they form the basis of what we'll call later on as moving average processes or autoregressive processes. Autoregressive is regressing of itself, so depending on previous values of itself. And this representation theorem, Wold representation theorem, is a moving average infinite and an autoregressive infinite representation. So this assumes that the current or the future value that you will see for this will depend on all the previous values that you have seen so far. And when you move one sample forward, it will depend on all the values that you have seen so far. So in that sense, they're infinite. Which also means, unfortunately, for truly estimating the whole decomposition of these, you need to have infinite number of parameters, which is not very helpful because we do not want to estimate infinite number of parameters. But in practice, with the time series that you work with, you'll notice that they decay. That is, their values become very small, and they're only relevant for the near past that you have and don't really depend on the origin time points.
So is the square summable part of what's the
Yes, the square summable imposition on the noise weights is part of Wold. So moving on, we will now start talking about autoregressive and moving average processes. So before we talk about them, there is another relevant operation which is often discussed in the literature or the theory of time series modeling, which is known as the lag operator. This is basically a shorthand for manipulating time series data, which says that when you apply lag operator on a time series sample, what it returns is the sample that occurred just before it. So it's essentially a tool for going back in time. And you can apply it recursively. So you apply it twice, you square it, but it basically ends up with you at 2 time samples back. And you apply it n times, you go back in 2 times. Its inverse is also existing, so you can go forward in time. Of course, this is helpful in forecasting, but in the series that you've observed, you can start at sample 1, apply the inverse lag operator, and move forward in future. Why this is helpful is it helps us neatly write some equations, as we'll get to. Instead of using large sums over infinite, we'll just write the lag operator or recursive lag operator. Just use that. Okay. So, and just as I said, so how using lag operator to write the whole decomposition. So we start with this time series, V and S, some of the deterministic and the stochastic components. Stochastic component is actually an infinite sum of noise terms. Since it's t minus 1, you can represent it as noise at current time t. So the noise we're observing now applied with the lag operator, and then we fold the sum into the lag operator and sort of parentheses or follow the notation. And this just says that this is the lag operator for all the time that you have observed the time series or it's observable. And so this symbol is equal to the infinite sum of the lag operator. And now, why was this helpful is right now, this said that the time series at time t was dependent on the noise terms at the time just before it. But now with this representation, say you can argue that the time series at time t is actually dependent on the noise at the current time, not the past. All right, so since this is an invertible operation, lag operation, so we can apply it on the other side. Here, we can apply it on the other side and we'll end up with identity. So this is the assume that the deterministic component is 0 for now. We just the series is dependent strictly on the noise component. We apply the inverse lag operator and we end up with something that looks like this. So a series with the inverse lag operator on xt.
psi star?
Psi star is to indicate the inverse of the square summable weights. And you apply the inverse on the other side as well. Since they sort of even out into identity or 0 lag operator, you end up with noise, theta t. Inverse on xt is essentially the sum of time series, and you can take it on the other side. And what you'll end up with is a infinite sum of in the psi weighted or weighted previous samples of X that you have seen. So through this exercise with the lag operator on bold decomposition, what we just did was, instead of calling it a sum of some deterministic component and the noise, which is varying, which is different for each time step, we can now write it as we can write X in terms of itself, hence the autoregressive part, and noise component at the current time. So with these manipulations, we were able to sort of write it in a more interpretable format for us, or something we can intuitively sort of understand and work towards predicting. So what the parameters here would be these side stars. Okay. So now comes the object of persistence. So far, we have been talking about time series that are dependent on all the samples that you have seen so far in time. But what if the time series that we're working with are dependent more on the recent past as opposed to everything that has happened in history? That's where the notion of persistence comes in, where we say that a time series can be made like a time series in future can be described by a function of only some finite previous values, not everything. And if we write it as it being dependent on just one previous value, then it would be, instead of an infinite sum, it would be one way previous value in some noise component, and which is again I and D, normal 0 sigma. And this is known as an autoregressive process of first order. First order because it's dependent on just one previous value. And because the bold representation term considered all values that existed in past history, that is now known as the AR infinite process, infinite or the infinite samples you've seen. And this example is AR1. One way I found this to be sort of intuitive for me to understand was think of it as a Markov process. You have orders of Markov processes. This is first order depending just one previous observation. If it were dependent on previous k observations, it would be a kth order Markov process or a kth order AR process. Yes.
We assumed our deterministic part is 0, right?
Yes, for this right now, for derivation purpose, we have assumed B is 0.
So we are modeling everything based on the
0. But for now, this is just to say that AR1 processes can be written through like bold decomposition with assumptions can be converted into AR1 process. For that purpose, we assume V to be 0, but for this to be applied, V does not have to be.
Yes. I was just a bit confused because we're modeling everything based on noise, right?
For now, yes. Well, with the bold decomposition, we said it depends on noise at all times. With the lag operator, we said, well, not all times. It can just depend on the current time noise and some infinite sum of the previous samples that we've seen. Okay. And that's where there was some, yes.
I say in our last special case, they are infinite, where the weights of previous data has a fixed relationship. Instead of the weights it's totally free, you can make the weights anything.
Yeah, precisely. So this is a special case of AR infinite. And where the weights, 5 star, of everything other than the previous sample is 0. Right? So just as I was talking about kth order Markov processes, if we have, for consistency with literature in this time series prediction space, if we have persistence on P previous values, you'd end up with a time series that's a weighted sum of previous P observations and noise at current time step. And this would be known as the ARP process. And just for some familiarity with this sort of notation and what it's called, the previous X observations that you have are called as the explanatory variables. So some libraries, they don't say inputs really when you look at them. They talk in terms of explanatory variables or stochastic variables. So if there is something if an input argument is an explanatory variable, it probably refers to the X's or the observations that you have in past times. All right. So we talked about how we can write AR1 processes, which is this. Now brings the question, how can we estimate the parameters or solve this equation for AR1 process? And first step towards that is thinking about recursion. So we just said that xt is equal to this, and depending on the previous observation. This previous observation would again be dependent on its previous observation. So recursion comes in. You can write it out like this. And here, we start to impose some constraints that the weights that you have should have magnitude less than 1. If that is true, then yes, X will converge. And this has an important relation that we'll get onto later with moving out of infinite processes. If the weights are not summing to 1, then the series won't be stable, and it would be non-stationary. This sum of weights is a criteria that you can quickly use to assess your model and how accurately is it modeling a time series and whether your estimate is stationary or not. So properties of AR1 processes. Since we assume for bold representation theorem that mean, variance, and covariance have to be independent of time. So we'll walk through slowly whether to ensure that each of these things holds true in case of AR1 process written out like this in recursion. In an AR1 process, mean is still mu. If we center it about mu, so x minus xt, the variance, that works out to be sigma squared 1 minus the square of the weights inverse. And I think you can walk through. The key thing to note here is the variance of the eta term noise is always going to be 0. But if it is weighted, it's 1. We do not assume sigma, we assume sigma to be 1.
That was an operator, right?
Yeah. And you can take it out here and you end up with this. Covariance of this, since we have an estimate of the expectation E, that is mu, we can substitute that in, and it again works out to a weighted variance of X. So key thing to note, all the terms in red, neither of them is a function of time, which is satisfying the bold representation theorem requirement. Or covariance station processing in general, mean, variance, and covariance are not functions of time. For AR2 processes, things get a little more complicated, and to solve them, it's easier to write them in matrix form, which is known as the Ewell-Walker equations in literature. X's are now written as Z's. This is to be consistent with Ewell-Walker notation. The noise is now written as V's, gamma is the weights. And if you write out the equation like this, you basically model the time series AR2 equation that you have over here. And to solve this sort of matrix and get the estimates of the parameters and impose the square summability constraint that we have, that they need to be summable and not infinite, we can compute the eigenvectors of this matrix, and these eigenvectors would have to satisfy a characteristic equation, which is like this. This is because if it satisfies this equation, then they will be square summable. So, and the eigenvector values would work out to be, sorry, I said that usually. But eigenvalues would work out to be this. This is basically a quadratic root. And if you, and these roots have to be less than 1. The eigenvalues have to be less than 1 in absolute to be for the weights to be actually square summable. So you can visit the properties later and visit Ewell-Walker equations, but most of this computation is now carried out by software libraries, which I think you're free to use for the projects. Okay. Talked about it. All right. So we talked about the deterministic component or modeling the time series with itself autoregression. What if the noise terms or the error terms, eta, they vary themselves with time? And a way to write them would be xt is mu. So deterministic component is now just mean or 0. and mean is there, and the previous error terms are again weighted by theta, and this formulation is for a moving average first order process because it is dependent on the noise one time step before. So with the bold representation that we had, it depended on the current time. But now, since we assume that noise itself is changing and we want to model that into the time series prediction that we're doing, we want to incorporate the noise at the previous time as well, weighted by a sample data. And again, both of these are IID and coming from normal. But for such a process, since these are zero mean, the mean is still not a function of time. Variance, when we work through it, and also they're not cross-correlated, so their covariance is zero. But this value is again zero, and when you have this square and this square, it works out. It works out to both. Variance is equal to 1 plus theta squared sigma squared. And both of these quantities are again independent of T, which satisfies that if you model, which satisfies the constraint for covariant stationary processes. And when you write out the x's or the time series as a sum of more than one noise terms, you're still not violating the covariant stationarity requirements.
So basically the noise, moving average capture non-stationary.
Yes, in noise, yes. Okay, and when we walk through with the covariance, for the covariance, fortunately, for the previous sample is theta sigma squared. Again, the math discussed for the variance applies here. Cross terms are zero, others are theta squared, sigma squared, whatever, and you end up with this. For covariance of lag with Q for Qth order processes, it works out to be zero. And again, whether zero or theta sigma squared, they're all independent of T. So regardless of how many noise terms you incorporate into your time series model, it would still be covariant stationary as long as the noise is zero mean and sigma covariance. And hence, all MA processes would be covariant stationary. Visiting the bold representation theorem again, now that we have formally defined what AR infinite and MA infinite processes are, V is a linear deterministic process V, S is the stochastic infinite moving average process of error terms, and what AR and AP look like. Now we can understand why the initial statement that bold representation is a linear combination of MA infinite and AR infinite processes, because it's dependent on all observations you've made so far in time. So, second.
Taking comments. Just give me an idea of what's.
Yeah. Go ahead.
So folks, just to give you an idea of what stationarity means and what wide sense stationarity means. Imagine into time series, right? A time series is being generated by some process. And so it's going to be something that's some time series. It can be varying in any which way, right? Now imagine all the alternate universes with the same process generated time series starting at the same time. Right? So this is the one, so the model over here is that this is the one time series that you're seeing, but then there's that, yeah. So there's an infinity of potential time series being generated by this process. And the specific time series that you see is one sample from this collection, right? So time is just another dimension, right? So in this case, if I look at this infinite collection of time series being generated by the same process, right? Then if I take a snapshot at this time, that collection is going to have a distribution, right? You agree? Right. And then I go back and take a snapshot at this point, that collection is going to have another distribution. Like tossing a coin. If I'm tossing a coin in a series, you're going to see heads, 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 tails, heads, tails, heads, heads, whatever, right? But in an alternate universe, would have had a different series of process, and yet another series of processes. There's an infinite collection of those, right? And when I say that the probability of heads is 0.5 at all time, what it means is that if I take this snapshot and look at what fraction of those were heads, that's going to be 0.5. And if I take this snapshot, that even there, the probability of heads is going to be 0.5. So this is a stationary process, which means that it doesn't matter where I take this snapshot, you're going to get the same statistics. Does that make sense? Right? So again, you're not seeing all of these guys. There's a hypothetical one where all of them happen. You're only seeing this one, right? But the assumption is that the distribution of across all instances is going to be the same. So not only that, you're going to have more constraints, because if the thing is stationary, then it means that the relationship between this guy and this guy over here, right? So if I look at this pair on every time series, I have this product, I have this product, I have this product, right? That has some distribution, that number. I can do the same thing out here with the same lag. This is going to have a distribution, that product, right? Those two will also be identical. So it doesn't matter how you look at it. If you look across all the infinite hypothetical time series, every statistic is the same across all time. That's what you mean by stationary. So that means you're really left in an interesting situation where if you can make a guess based on this one observation about the entire process, that guess is going to hold for all time. What he means by a covariant stationary process is this, that if I look at this collection, right? And if I look at this collection, they may not have the same distribution, but they will have the same variance, right? Not only that, if I look at this pair of samples, and I treat them as a pair of variables, right? And if I look at this collection, and if I look at this collection, the covariance matrices are going to be the same. Okay, so why is that helping? Can anybody tell me why that would be of any help? Yes.
Also, covariance for the node in particular.
Yes.
When the autocorrelation, because sometimes it changes very fast and sometimes it's fast. So if you plot it, it could either.
But the point is you're giving me engineering solution answers, right? But here is the point. Why does stationarity make sense? If the thing is stationary, right? Then it doesn't matter whether I'm looking at this collection or whether I'm looking at this collection, they are the same. Right? This collection has the same distribution, sample by sample by sample. These are IID. So if I look at this, it's like tossing a coin, right? So these are infinite different instances of tossing a coin. But then if I look at all of these coin tosses, or whether I look at all of these coin tosses, they will have the same distribution because it's stationary. It's not changing with time, right? Does that make sense? Okay, that makes sense. Okay, so now wide sense stationarity is going to say this. If I say it says that the covariance doesn't change with time, which means that if I look at any pair over here across the set, that covariance matrix is going to be the same as looking at that pair across the set. Right? Which means that now I can just take this pair, treat them as a sample, take this pair, treat them as a sample, and I can take pairs of samples scanning across time. And that collection is going to be identical to, statistically identical to taking this collection across the samples. And so now I can use this collection, which came of just one observation sequence, and make a guess about the entire ensemble. Make sense? Right. Then I can use the yeah.
The example about where the distribution might change, but the covariance is stationary.
So, can you give me an example of where the distribution might change in the point sensation process? Or covariance
Distribution will change with time.
and the covariance stationary process. If you ask me something on the top of my head, I can't give you something because I've been thinking about it right now. But most processes in the world are going to be like that, right? Meaning, if you begin looking at third order moments, the third order moments may not be the same across time, but the second order moment might be the same across time. So, right?
Yeah.
In the case of means, it's very obvious. A random walk, the variance is going to keep increasing with time, but the mean is always the same. Like a drunk person walking, right? A drunk person walking is going to be starting at some point. Then at each point in time, he takes a coin flip to decide whether he's going to go north or south. So he may go here, right? So at this point, the variance is 1 across all the. Each of these is a drunk. So I've got a whole ensemble of drunk people. They all went to the bar as a giant party, and now they came out and they're all walking, right? And each of them has their own coin. And so they start here as they flip a coin, decide whether to go left or right. So at this point, they all just came out of the bar. The variance is 0, right? At this point, is the variance going to be 0? Right? At this point, from here you could go here, this guy could go here, this guy could come back here. At this point, is the variance going to be 0? Well, how does the variance here compare to the variance here? It's going to keep increasing as you go over time. But what about the average value? The average value is going to be the same at each time, right? For every person who went north, one person went south. So now you have the mean that's constant over time, but the variance can be increasing over time. But again, you have to think about the collection of drunk guys who came out of it, not that one guy who came out of it, right? Anyway, go ahead.
These two are the correct concepts.
Thanks.
Moving on, combination of autoregressive and moving average processes, how we can put them together to model time series as accurately as we can, and how do we use this information in forecasting. So, ARMA, as the name suggests, is putting the autoregressive and moving average processes together. So now the X time series you have is no longer dependent on only the previous samples or autoregression, but also on a one error sample moving average. So ARMA 1.1, following the notation of moving average and AR processes, it is dependent on previous sample and the previous stochastic noise. And with the lag operator, we can write them as such. And more generally, with these, we can start the model ARMA 2.1, which would be second order autoregressive, so 2 terms of previous X's, or in 1 term of noise, and or whatever variation you want. So more generally, you can model ARMA PQ processes. And this is an example of ARMA 1.1 process simulated. So we did, as you can see, with some regression, like first order regression, and some noise terms, this is a fairly complicated time series that we can simply model through the ARMA 1.1 process. Moving on, so more generally, ARMA PQ would be a lengthier term, and it could again be written like this. And again, as I said, lag operator allows us to write the thing more conveniently, not through a sums. So it ends up being fairly convenient to write like this. And one thing that this is again ARMA simulated ARMA 2.2 process, so order 2 in both moving average and autoregression. But it's sort of difficult for at least me to intuitively make sense of this because they both look very similar in the sense they're just varying in time. But I think that's the noise at play. And we'll visit these figures again later on and talk about in terms of autocorrelation that they have with the previous sample. And there it becomes much more clear why these are ARMA processes and not just random non-stationary processes. All right, so going back to the ARMA 1.1 process, which can be written like this, and since inverse exists, we can move the lag operator to the other side and think about the writing the ARM process as basically a sum or a geometric progression. And here the key thing that I want to highlight is that these have to be square summable still, and the variance and covariance still have to stay finite, and they will because they're linear combinations of previously observed autoregressive and moving average processes. Now this brings another important question. We were talking about that these have to be square summable and all those things, but we didn't really talk about how do we estimate these parameters, these numbers that we have. And for this problem, MLE, maximum likelihood estimation, comes into rescue, or negative log likelihood estimation, depending on how you structure the problem. But through this, we can estimate the parameters size squared, or most of the algorithms use this to estimate the parameter size. And these we constrain by applying the square summability constraint on them, what is being estimated. And this is how you generally end up with the estimate of actual model parameters for an ARMA time series or AR time series. Walking through this, for a time series, given an initial observation, probability of the future of and the parameters, probability of the future observations can be written out like this, and log likelihood would become this term, which is dependent only on previous x's, and they are initial estimates of the weights. And since this is a quadratic term, you can minimize this by b, which works after this ugly equation. Again, you don't have to implement this. This is done in the back end by libraries, which you can use, but it's helpful to know where all of that is happening. Step, you get estimates of this. I think a more important observation would follow here. Yes. So is the MLE of the model parameters actually the forecast, right? So this is a quick little proof on that proves that the minimization of error that you have from previous observation is indeed equivalent to forecasting. So you forecast a value x star p plus 1, and there is a true observation of x star p plus 1. Is minimizing the difference between them indeed forecasting, which intuitively makes sense if they are the same thing. And yes, we are correctly forecasting, but you can prove that in terms of expectation of the mean squared error through squares. And at the end shows that the minimum for this term would be obtained when z is equal to the actual observed xt plus 1, or z, which is the x star. So that's a bummer, but so we can skip past this. And finally, we're on to non-stationary processing. So first question before we get into non-stationary processing is how do we even tell whether a process is stationary or not? What are the tests that we have? And there's a rich body of literature on them, but the most important, as we've been discussing, is the square summable, the way it should be square summable, or magnitude is less than 1. And I think this was my interpretation of origin of these stationary tests. This is mostly done in economics or statistics domain, this sort of forecasting, and they all like their hypothesis testing. And that's how most of these tests are structured or formulated, or literature on them. So one of the basic tests for a given autoregressive process is you assume a null hypothesis that the process is non-stationary, roots are 1, and the first hypothesis, alternate hypothesis, is that the square summable or magnitude less than 1 and they're stationary. And this is known as the autoregressive proof test. You can implement this yourself. Again, libraries also do this for you, so you can use those. As an extension, people have worked on their variations where your null hypothesis is that the series is non-stationary. You have a test where null hypothesis is stationary. So you can use some of these or any of these tests to test the time series that you have. For example, in context of your projects, the air quality index or the exchange rate for the different currencies is the data that you have for them when you fit an ARMA model. Is it a stationary time series or not. And then you you tweak the parameters of it. And when we'll talk about non-stationarity and how we can address that, you employ some of those techniques, does the data become stationary for you to apply these techniques? All right. So this brings us to what if a process is non-stationary? So we talked about random walk and how that is a non-stationary process with variance that depends on time. So mean is 0, but the variance, since it keeps it's dependent on the variance period time. So before, it's a function of time. So this is not necessarily a station. Random walk is not a stationary function. So a stationary process is covariance stationary if these conditions are met. Random walk violates this, but if any other process that you can imagine would violate any of these requirements, then it would be a non-stationary process. So I was talking about these ARMA processes, right? The ones that I showed. So if you compute their autocorrelation, I think because of noise, there is some small variation, but you notice that their autocorrelation dies down very quickly in both of these. In first order, it dies down much rapidly than the other ones. What this says is it depends only on very few samples just before, and for AR2 process, it depends on many more. If we look at, yes, the non-stationary processes, for a non-stationary process like random walk, autocorrelation is somewhat high for the whole time that you're observing the series for. For a random walk process with a trend is basically adding one value to it. For example, the random walk example there, they were at the current position, but this is saying that they're always moving in a direction. So there's always a sum toward or a trend to move towards a direction. A constant is always being added at a given time. That is a trend. And then it's a random walk process about that movement. And that still has a high autocorrelation. So these values are dependent on many, many more before its time. So they are non-stationary processes. And that got messed up. Fix this slide order. But that brings us to an important question. How do we deal with processes that are non-stationary and that have trends in them? So for this for the context of this lecture, we'll confine ourselves to trend behavior, that is a constant value is being added to the series that you have. And the method to fix it is known as Box-Jenkins method. And a very simple way to understand it is in the time series we have, which is non-stationary with the trend, we simply try to remove the trend so that the resulting process is now stationary. And how do we remove that?
Specifically refer to the random walk, right?
Yes.
So again, going back, just consider we have here's a simple example. Right? You've got our drunk guys who all came out of a bar, right? So we have this whole party comes out, they're all drunk. And so now they're all in the same location. At this point, what is the variance? Their positions. 0, right? Then first time, the first one, each of them flips a coin, right? Can you show your laptop? Thank you. And so if they flip a coin and they all turn up heads, or probably not, or it's definitely not. Right? Very unlikely that a million people toss their heads, coins and all turn up heads. So then this guy goes here. This is showing the time, right? Maybe this guy comes here, and this guy comes here. So what is the variance now? Is the variance 0? Not 0, right? So variance change with time, right? Then they all flip a coin again. Maybe this guy moves here, right? Maybe this guy moves back here. Maybe this guy moves back, right? What is the variance? Is it greater or even less? Even greater, right? But what about the mean? This is a stationary process.
No.
This is a stationary process. Why is it not? The variance is always changing. How do you convert it to a stationary process? Can you say that loud? If I only record the change, right? So the current position minus the previous position. What is that going to look like? It's either +1 or -1 at each time, right? Does the distribution of that change with time? No. The variance is always going to be the same, right? The mean is always going to be the same. Is that stationary?
Yes.
A simple differencing process to this non-stationary process and made it stationary.
Okay, so we just discussed the differencing method. So if a process xt has a linear trend in time, then by this differencing operation, we can obtain a series delta xt, which would not have the trend and would hence be covariant stationary for us to work with. Process can have a quadratic, so this was for linear trend, it can have a quadratic trend, and if we address that through this second order operation, then it becomes delta squared xt, and then delta x squared xt would still not have trend. So how does that actually work, or how does differencing work? For first order differencing, we define a differencing operator delta xt, which is equal to x minus xt minus 1. Basically, we're removing the previous sample, or as we discussed, keeping the distance between the two observations that we have. So delta x here is known as the lag operator. Delta x here can be written in terms of the lag operator. Again, a shorthand for preventing us from writing really long series. So delta x would be second order, which again would be like this, or in terms of lag operator, you might write it as a square of one of these lag operators. Now, for an ith order trend, you can define ith order delta x, which would be again in terms of nth order I. Now, I wanted to give an example of trend removal by differencing. So here is a non-stationary process with a trend TD that is a deterministic linear trend depending on time, A plus BT. So this is a linear trend. And this is an AR1 process. And the moments are that expectation of this is A plus BT, and the variance of this is not dependent on time, but the mean is. Now, if we look at delta x, where x minus xt minus 1, so you have TD at time t, TD at time t minus 1, the time component in this equation would cancel out and would be removed, and what you'll be left with is a process that is no longer dependent on time as the first initial one with the TD A plus BT was. So delta x is now B plus this term of lag because of differencing. And this series is now covariant stationary, even though the original series was not. And while you cannot directly estimate xt, you can estimate the difference delta xt's through this differencing operation, and then you can you can do forecasting based on delta xt. So instead of predicting the actual series, you predict the distance in actual series, or distance in samples. Now, with the ARMA model that we had talked about, there are implementations which incorporate the differencing, which is represented through the I. So ith order differencing can be incorporated into the ARMA model, resulting in what is known as the ARIMA models or integrated ARMAs. So these now are written with a shorthand called PQD. So P for ARMA, for autoregression, Q for moving average, D for the differencing operation. And so there are some practical challenges to this. First is it requires you to have some knowledge on what sort of a trend you have. Is the trend linear? Is it quadratic? Which would determine what sort of differencing you would need to do. And is this trend present in a deterministic component, stochastic component, and so forth. Then, now, while ARMA PQD required you to estimate PQ parameters, now you have to estimate D parameters as well, which is like the differencing operation. And this creates a really complicated choice in what sort of a model selection to use. And you may want to use multiple different models or empirically test, which results in least forecasting error for you, and actually use that in your projects. For example, the time series you have with exchange prices, you run that many times, different models with PQD, and you see which one works best for you. And eventually you'll find one that that would explain which order differencing would work best for the type of data that you have and what sort of autoregression and moving average error terms that you actually need. Oh. This brings us to this question.
You know, we should put those
QR codes. I think the application we use, TinyURL, gives out QR codes as well, so we can copy paste that next time.
QR code.
Thursday we can do it. But we need to make polls a day before so that the site can be fixed. All right, so we'll move on. And so the question was, can any time series be made? Answer is false. So while it is helpful tool, it helps you remove a lot. So basically, lag operator or differencing method allows you to remove trends. And some time series may be non-stationary, not because of the trend, but because of other reasons or of their distribution. But even sometimes you have trends which you cannot remove by differencing. Yes. So limitations of differencing, trend removal in random walk. So in random walk, we have white noise being added at every time. And if we apply so now the trend is in the stochastic component over here. And even when you try to remove trend in the stochastic component, the variance would still depend on the time. And as a result, no matter what sort of differencing you apply on random walk, it would not become a truly stationary process. And stochastic trends are very difficult to remove, which is why some of the series that you work with cannot be made perfectly non-stationary. And this plays a lot into the project problems that you have. For example, the price stock market prediction. If you have one of the variables that you did not measure with it, for example, we are predicting exchange rate, oil is very strongly correlated with it, maybe gold is as well, and you did not consider gold, and that is now being folded into the noise term. And of course, there's other noise being added with social and global current events and all of those things. No matter how much you tried in that noise component, differencing cannot account for everything. And even with highest order of differencing, you may not be able to remove all the trends completely. And then these sort of stationary models that you use for prediction, ARMA and ARIMA, won't be applicable in the time series that you add. But yes.
It's how to calculate the gradient of noise.
Gradient of noise?
So like noise, the random variable.
Mm-hmm.
Yeah, then like how to calculate the gradient of the noise.
Would noise really have a gradient?
Yeah, I mean, if it's just a random term,
Yes.
follow a normal distribution.
Right. So you mean when you apply trend removal to the noise terms, what happens?
Yeah,
right?
I mean, if given a random variable made by some like normal distribution, sum of normal distribution, how to calculate the distribution of the gradient of the variable?
Just like an assumption.
Yeah, and when you do the differencing operation, it would still result in a noise term, right? It would not become deterministic. So if you had noise right now, which is dependent on time, you have noise in future, you sort of take the difference between them, and then you move forward in time and then take the difference between them again. It would not be the same, it would change because they're noise. So even the differencing operation, it would still result in noise. So that's why if there's a stochastic trend, then that is very difficult to remove by differencing. The trend has to be deterministic. That is, every time it happens, it's of the same distance. If that distance varies itself, no matter what sort of differencing you do, it will result in noise again. So you cannot really remove it.
If the noise is stationary, that's it's perfectly stationary. And you perform a differencing operation on it, all you're doing is doubling the variance. So every time you perform a differencing, you doubling the variance, right?
All right. So as a last slide, the application of what we discussed, it's helpful in the projects that you have. You can think about this. I personally used the ARIMA models last time when I was doing the project for this course, which was stock price prediction. So I think it directly applies to these two problems. Not so much on blind source separation, but at least for these two. Parameter estimation, most of the libraries carry it out through MLE. You can get more into the theory of it, but that's all there is. Now, we just talked about single variate ARMA models. There's also a variation of multivariate ARMA models, which is known as the vectorized ARMA models. And there's also something called the dynamic ARMA models, which is very helpful in the sort of projects we have. But yeah, and careful about the sort of considerations you're making regarding the deterministic and the stochastic variables and the decomposition of the time series that you have, because your assumptions will directly influence the kind of predictions that you make. Okay, yeah, these are the sources that I use to design these slides.
Again, if there's a lot of math over here, but if we want to see a picture of what he's talking about, then it makes pictures often convey the story. So here's what we're really assuming. Consider the stock market.
I think
I'm looking at the stock market, consider a particular stock price. Then this is stuff. So this would be the stock value across two, right? But then there are other variables that are influencing the stock price. A stock value depends on itself. It also depends on other things that are happening in the market. It's something kind of right? And that and what is the now, if the stock value for any particular stock is stationary, meaning you can't really, it's not fixed, it's not a fixed trend, it fluctuates. But then it fluctuates in a manner where if you pick the same stock, many instances of the same, if the same process happened a billion times and you took snapshots, the statistics would all be the same, right? So what Wolff's theorem says is that the stock at this time, it can be explained as a weighted sum of all of these guys and these guys. Right. So Wolff's theorem literally states that if a process is stationary, which is an assumption that we often make over here, then the value at any time can be thought of as a linear combination of all previous values and all previous innovations, the things that actually make the value change. Right. So, because if this thing never changed, if there were no innovations, it's going to be constant, right? Now, for this process to be stationary, this cannot blow up, correct? And so what this means is that these values, these weights with which these guys are summed cannot be arbitrary. These weights must be square summable, which means that, even though I'm taking a weighted sum of the infinite past, the value stays bounded, right? Same thing about these weights too. They must really be square summable. Now, what this means by square summable is that if I took these weights, then this is history. We're to find that the weights have to fall off like this, otherwise they will not be square summable. Okay, so in which case I can assume that, yeah, I know it's dependent on all these guys, but I'm going to assume that there is no dependence. Right, and I know that it's dependent on all of these guys, but I'm going to assume that these are the only dependencies available, right? So then this is an autoregressive model of order 3, and the average model of order 2. Right, and so this is a perfectly good assumption to make about most processes which are stationary. You've got to figure out exactly what is the optimal combination of autoregressive and going average terms. But then processes are not stationary, like the trunk and guard, but still can still be very predictable. And so the ARIMA model basically says that, in addition to this, there's a constant trend guy, and these trends are a nice function. They're not random at all, right? And this trends will also be added in. And through a differencing operation of some kind, you can get rid of this guy. And then when you get rid of these guys, these are the only two things remaining. And then you can learn your AR model, then use that to make predictions. But you're really making a predictions to make the prediction, then you want to factor in the next trend as well, right? So that's basic idea, pictorially, right? And all the rest of it is a whole lot of fantasy. Why is it the case for the case for the fancy thing is that the city model that I just drew on the board, it explains most processes in the world to a high degree of precision, but where the error doesn't really explode, right? So, which makes it really good for predicting all kinds of interesting phenomena like the stock market. Can I go back to the slides? Yes, the slides, which were very nice. So there are two kinds of predictions that one likes to make. Now, if you're a better in the stock market, right? What are the kinds of predictions you want to make? You want to make predictions about and so that we can make money in the stock. But maybe you also want to make predictions about extreme phenomena. Do you see some extreme phenomena in this picture? The spikes are extreme, right? So there's a whole theory to it. It's called extreme value theory, which is about predicting those spikes. They are rare and they don't happen all the time. But when they occur, they're going to have an extraordinary influence on the world. Right? And all of the trends that you're talking about, stationarity and so on, you're talking about capturing everything that happens within the bound of one standard deviation or two. Those guys are way outside. So can you give me some examples of extreme phenomena that happen? Oh, wait. Something else? Why is it all illnesses? And it's something else. War, earthquakes, natural disasters, storms. These are extreme phenomena. They're very rare, right? Each disaster that happens is an entirely different one. Or maybe, the Pirates win a baseball game, right? Extreme phenomena. So these kinds of things happen. And if you're able to predict their occurrence, can you imagine how much money you would make? So there's a whole theory on extreme value, predicting the upper things. And what he's spoken about is predicting everything that happens within a standard deviation, right? And so this model is really good at predicting the node. And for pretty much most of your homeworks, the projects, this would do it. Anyway, thank you. Give them a hand, folks.